Alright. We're going to talk about non-Euclidean geometry today, which is a topic because geometry is really lots of history. So let's get into it. Whatever.
First of all, you see this man here. This man is Euclid, yeah? Come on. Main facts about Euclid: 300 BC in Egypt, and he wrote or compiled this book called Elements, which is basically a textbook of the time with loads of different maths techniques from other mathematicians. So yeah, these are just like fake images, they're just drawings of what people think he looked like, and he looks like an unk to me. But yeah. Okay, so Euclid has 5 scams. First of all, he says a straight line segment can be drawn between any 2 points. Next, any straight line segment can be extended indefinitely into an infinite line. Hopefully you guys understand what's going on here. 2 points and a line, and we just extend that line further. Next, given a straight line segment, a circle can be drawn having the segment as a radius and the endpoint at its center. So this is basically the definition of a circle, just a consistent radius, shebang. Also, all right angles are congruent. To us, this is common sense, like a 90-degree angle here is same as here. And finally, the 5th scam is that if a straight line intersects 2 other straight lines and the interior angles on one of the sides sum less than 2 right angles, the 2 lines, if extended indefinitely, will meet on that side. I don't understand what that means. No one really understands what it means. Fortunately, we have 2 things. First of all, these are not called scams, these are called postulates, from the Latin word postulatum. It's just the starting point of this geometry. Yeah. Secondly, nah, it's gone. Secondly,
yeah, so like, remember the 5th postulate? That's actually been concisely formed by Plaisware, and it's actually an axiom right now. And it's basically, you have a line and a point. And in Euclid's postulates, it states that there's only one possible line to draw, such that both lines are parallel, which is obvious. It's not too obvious, but when you think about it, if you have only one line, you can't make any variations, because when you vary it, you're going to intersect with the other line that you originally have. But there's only one line that's possible. Yeah, and that's Plaisware's axiom.
Okay, so a little bit of the timeline. Across 2,000 years, mathematicians thought the postulate 5 must be derivable from the others. So first this guy tried, then this guy, and then this guy, and then also this guy as well. And you may remember, like, there's this guy from...
Yeah, he has... all of these are famous mathematicians, but they're too weak to tackle this problem.
And what's the function for that?
This one, he invented a Lambda W. Sarachi's rectangle, if you know about that, is one specific case that tries to prove the 5th postulate, but it does not work. And then these 2 guys are part of an academy, I think, from Euclid.
Everyone failed. Pretty sad. Basically what it shows is, as far as we know, postulate 5 is a completely separate postulate that is needed.
Yeah.
So what is geometry?
Yeah, so what is geometry? We're talking about geometries for such a long time. We want to restate the problem, right? So a geometry is a set of properties about objects, which points and lines. That's what we're going to focus today, mostly points and lines. With points and lines, you can make a lot of stuff. Shapes, surfaces, bunch of stuff. But today we're going to look at some models of geometry. And the model is just, you have the points and lines, and there's axioms, which are the rules that these have to satisfy. And we're going to investigate what happens when we have different rules. So let's go on.
Yep, one of the most basic forms of geometry is incidence geometry, in which everything satisfies the following axioms. 2 points determine a unique line. Each line contains at least 2 points, and there exists at least 3 non-collinear points. First 2 very simple. Third one is basically saying these 2 are collinear points. If we put a point over here, it's valid because it's not on this line, and there is at least 3.
Yeah, so the point of this is, if you have every point that's collinear, it's just be a straight line. There's nothing interesting about that. Right. We want to investigate interesting math, so let's go.
Perfect. Now we have some questions for you.
You can answer.
Is what an incident?
So let's try to answer these questions.
Is this an incidence geometry?
Any answers?
No, it's not. Because the 2 points do not uniquely identify a line.
Alright, correct.
Very correct.
No.
Same things.
I think same thing, but
They're
there's probably
collinear
more,
points. There's a point which is collinear to two
Wait.
others, isn't there?
right? Wait, no, it's true.
Oh.
It's incident geometry. There's no 2 points that like have different lines, right?
Is there a point that's collinear to two others?
What?
On that straight line
That
segment?
doesn't discount it from being incident geometry.
Oh,
Any 2 points are connected by Yes.
Because basically that, obviously on this line for example, we could just put a point here and it could still be instance geometry, but the whole point of that rule is that if it was only collinear points, then it wouldn't be instance geometry.
oh.
Okay, a new question here.
Is this incident?
Is this instance geometry?
Sounds pretty cool.
Let's say yes.
Anyone else? Any opinions?
Wait.
Yeah.
It's like a
It's-
graph.
It is like a graph.
It is a graph.
Like technically everything here is a graph, but graphs can have more than 2 different ways of connecting 2 points. So it's a special type of graph.
Yeah, it is.
So this is actually incident geometry. And this one's very famous. It's one of the first ones that Fano discovered. And anyone tell me what's unique about this one? It's very symmetrical. What's so unique about this form? Because you could draw any other incident geometry like we did the last one, but this one's unique.
It's like the maximum something.
Ryan, if you answer.
Maybe think about like how many lines are from each point, how many points are on each line, stuff like this.
Oh,
Yeah.
3 and 3.
So we see each line has 3 points exactly. Each point is incident on 3 lines. The word incident just means that 3 lines passes through it. And that's pretty cool because if you see, this is the line technically. But
Now
Let's do
we've
it.
got our favourite question. Is this incident geometry?
this one's pretty cool as well.
Oh my god.
no.
Why is there no point there?
It is actually.
Yeah?
I don't think it is. Because those 2 points are collinear.
Oh, okay.
Let's see. It is.
It is.
And this one and the one before is something called partial geometry, which is a more specific rule set that all of these have to satisfy. And the general basis is each line and point has a specific number of stuff. So like in those 2 examples, each of the points consists of 3 lines that incident it, and each line has only 3 points. And those 2 are actually different, or they're different models, but they also they satisfy this thing. So it's pretty unique. And let's move on to talking about what we're here today. Non-Euclidean geometry and parallels. So we talk about this again. Or Euclid's 5th postulate, the parallel postulate, states that there's only one unique line, which is parallel to a given line at a point. And now let's try to change this rule, because now we know that it's unique. It's not like a rule that you could change that rule and you could get some interesting geometries from that. Let's see what kind of geometries you can get. So hyperbolic geometry states that instead of having one exact line, there's infinitely many lines that do not intersect L. So if you have a point in a line, you could draw any other line, infinitely amounts of lines, that's such that they never touch each other. Okay? And elliptic geometry is the opposite, where every line through that point touches L, no matter how hard you try. And then you can see that these make up different geometries. We only change one single thing, and this turns out we have a lot of geometries now we can investigate. So what kind of geometry? So Euclidean geometry is the one that we're most used to, where every single line that is parallel have the same distance between them, and they're perpendicular. They have the perpendicular between them is the same. But for hyperbolic, the perpendicular distance between the line and the infinitely many lines increases. This is why that if you have 2 lines in the hyperbolic plane, one line diverges off, so you're never going to touch it, and it's every point as well. And oppositely, in elliptic geometry, every line converges to the other line. So every point on that line gets closer and closer to the line that we don't intersect, and that's why they always intersect, no matter how hard you try. And we're going to talk about hyperbolic and elliptic more in detail later on, but we see there's very special properties about them by just changing one postulate. So let's look at the history of discovering this.
A little bit more history then, yeah. So Gauss primarily developed non-Euclidean geometry, but he was a bit scared to tell everyone because it's a little bit radical and people would think he'd be smoking a little bit too much chalk nuts, a little bit of magic stuff. But then independently, Lobachevsky published his hyperbolic geometry independently in Russia, and similarly, Bolyai published independently in Hungary. And this is quite interesting that they happened all within like this period from 1820 to 1830. Like it's kind of such they all happened independently during this time. And then Beltrami proved the consistency that there are actually all possible geometries as long as like one, yeah, 4 rules are kept and one is changed. So yeah, quote from Gauss: the assumption that the sum of the 3 angles of a triangle is less than 180 leads to a curious geometry which is self-consistent. So this is a little taste of what is about to come.
Yeah. So let's look at angle sum of triangle and how that links to Gaussian curvature. So angle sum of triangle, everyone knows in Euclid, it's a plus b plus c equals pi, or 180 degrees. And that's very obvious, because no matter how you draw a triangle, it must satisfy. But in spherical, it's actually greater than pi. And in hyperbolic, it's less than pi. And let's see why. Right? We've got these representations, so that's Euclidean, that's spherical, and that's hyperbolic. And the way that I think about it is being on the sphere and being on the hyperbolic plane. So the inside of the sphere, that's how I think about it. But how can you describe these concepts more mathematically? And that's where Gaussian curvature comes in, and the constant. So if we look at how the area changes, this obviously gets bigger, right? This obviously gets smaller. How can we quantify the change in area? That's where we use Gaussian curvature. So the formula is the curvature times the area is the excess or the missing angle from the triangles. So if it's Euclidean, it means that there's no excess angle flow. There's no overflow or underflow from the angles. So the area is always going to be, the k is always going to be 0, and area is the same as the area. But if there's overflow of angles, so you see that this angle obviously bigger than 180, then there's going to be an excess area. And that excess area is directly related to k. And since the overflow is positive, k is greater than 0, and the area is going to be larger than what it is originally. And oppositely, we have hyperbolic, where the angle shrinks. So this means that the area is going to be smaller, right? And since the overflow becomes underflow, it's negative, the area will have a negative scale. So the Gaussian curvature will be less than 0. And that's how they quantify these ideas mathematically. And there's actually a lot to do with Gaussian curvature and a lot of other sides of math where they explore more into geometry. But we're not going to touch too much on that today, because there's a more overview of what is it. So first, we're going to talk about spherical geometry. And now we have a sphere, which is S2, and it's in R3, where every point is distant R. So it's basically a circle or a sphere. And show the picture. Yeah. So the lines are replaced by great circles. And the great circles is this. Is where the radius of a circle is exactly the same as the radius of the sphere. Or the diameter of a great circle is exactly the diameter of the sphere. And the small circles are just the smaller ones on top. So it turns out that there's a lot of real-world application, because the Earth, as you know, is a sphere. It's not flat, right? And we can apply what we have for spherical geometry on the Earth, because we know a lot about the Earth, but not a lot about spherical geometry. So if we walk in a straight line on Earth, obviously we come back when we go one loop round, right? So it means that lines are replaced by circles in spherical geometry. And they're actually great circles. They're not small circles. Because to walk in a line on a small circle requires you to walk not in a line. So you're not going straight every time. And that's super interesting, because it means that every point has many great circles through it. And every pair of great circles exactly intersect in 2 antipodal points. What this means is just opposite sides of the sphere. And there's no parallels, because every other line will intersect. Angles on the sphere with a triangle always add up greater than pi and has the area which is r squared times the axis. And the reason that is, I'm not going to go into it, but it's very interesting. I think you could derive this by using some probably calculus, but it's interesting. And remember that every point has constant curvature k, this is greater than 0, which means that how do I think about this is every point converges to each other. So it gets closer and closer. And imagine a sphere. So like if you just walk off a sphere, you have to curve in. And that's what curvature of greater than 0 means. And you see that there's a lot of real applications. So if you ever book a flight across the continents, you usually see that it's not a straight line. You actually go on a curve, which Brian's going to explain more.
Exactly. So, especially here, we noticed the red line is a straight line between Florida and South Africa, whereas this blue line is actually got a fancy name, but this is the shortest route possible to get from there, and it is likely what your airline will take you through. Does anyone think they know the name of this type of line? Yes, sir.
Geodesics.
Oh,
That was beautiful. So yeah, geodesics are these curves, the locally minimized distance between 2 points. But additionally, there's a little catch on this, because if we look at this interesting plane from the imagination, we notice that this is a geodesic, even though it's actually a lot longer than these other paths. So the second catch on this is that its tangent vector must remain parallel to itself along the curve. So effectively, if you were driving along in a car, you wouldn't want to turn the wheel or anything. Again, in hyperbolic geometry, they're just hyperbolic lines which intersect the boundary orthogonally.
yeah. And this is going to come after we talk about hyperbolic geometry.
Yeah.
So remember that, we're going to come back.
So, a bit more on this. This is a line of latitude or longitude, who knows? Yeah, I don't know either. Okay, yeah, line of latitude, exactly, you're correct. So, the reason this is not a circle is because you can convert it into an extrinsic line, yeah? If you just place the cone on top of there and like copy the line through. And when you unfold this cone, you're going to be left with this curve here. So this would form a circle, but if that were to be a geodesic, it would form a straight line. So we can prove it like that. A little bit sussy. Hopefully.
Then it would have to continually keep turning, just as if it were driving in a circle. Now, the entire
Yeah, exactly. As this guy's saying, to go around here, you'd have to keep turning your car because it's not actually a straight line.
That's the reason why small circles and great circles are different. Great circles are the lines in normal Euclid geometry, and small circles are the circles in normal geometry. And they're distinct. Alright, so let's talk more about spherical geometry properties, right? So now, we know that if any two great circles intersect, so two lines intersect, they're always going to be opposite at top. And it's not too intuitive, but it just happens because they are the diameter. And two distinct, this could be also said another way. So if you have two distinct points that are not antipodal, then there's only one great circle. Because if they are antipodal, there's two or many infinite of them. Alright, let's move on. And we talked about the angles, and let's just talk about it a bit more. So any three great circles, there are not unique points intersect to form a triangle, right? An angle sum of a triangle must be greater than 180, but also less than 540. Because if each angle is 180 degrees, they at most get 180. Like 180 times 3 is 540. So that you can't really have bigger angles. That's not a triangle anymore. And the area, I just talked about that as well. It's proportional to the axis angle. And you could do some calculus to work that out and figure out why. And this is the interesting part. Two triangles with the same angle sum, they're equal in area. So, even though if I change one of the angles and I change all of them, such that the same area, or the same angle sum, they still have the same area, which is a unique property of spherical geometry. So now let's move on to hyperbolic geometry, which is basically, I think, inverse of the spherical geometry, because everything else is the same, but only the curvature is different, and it's negative, which means that instead of curving downwards when you walk off a sphere, you curve upwards. So you get away from the center of the radius. So if you think about a sphere and its center, every time you walk on the sphere, you're the same distance, but you actually get closer if you just go like that. But oppositely, if you look at the Pringle just now, it's going the opposite way. Yeah, so this will be an example of parabolic. But actually this is spherical, so it's not a good example because it's really hard to imagine what it looks like to have everything being parabolic because we don't live in the parabolic world. We live on the Earth. But the unique property of this is there's infinite parallel lines, which are called hyperparallel. What this means is there's infinite lines you could draw, which they do not intersect anywhere. And similar to spherical, you could draw 3 lines that intersect, and their angle will always be less than 180 degrees, but no more than 0. And the famous thing to represent parabolic is the Poincaré model. This basically what it does is to represent parabolic geometry with straight lines that are orthogonal to the circle here. So these lines are straight, but because how it looks when you put it on the disc, it looks curved. But actually, if you just keep on walking, it will be straight. That's how they represent that. And this, has anyone recognized this? Does this look familiar to anyone? Right. It's M.C. Escher, a very famous mathematician or artist, who uses parabolic and spherical geometry in his art. And we can see that this is just exactly what we talked about, where they use the Poincaré disc model to draw art, which is very satisfying because it's very symmetrical. And the circles in parabolic geometry, and circles are just points that are equidistant from given points. So in Euclidean geometry, a circle is a circle. That's obvious. And we talked about, in spherical, a circle can be a great circle or a small circle. But the great circle is actually a false circle. It's just a straight line. But in parabolic geometry, there's actually 4 distinct different kinds of circles. And these are circles, borocycles, hypercycles, and geodesics. We talked about geodesics a bit already, and it's the same idea. But let's start with the circle. So, I'm going to point out this is a Poincaré disc. And what happens is, if you look at the actual Euclidean origin, it will be here. But the hyperbolic origin is a bit different, because this is a straight line, remember? So the origin is equidistant from this guy, instead of actually here, where, yeah, and BC is the diameter. And that's just how it looks. And a circle is just where it's inside the Poincaré disc. That's what a circle is. A hypercycle is a bit different. It's where there are the lines that are equidistant from a point. So those don't have to form a circle. They are a circle because they are technically equidistant from everywhere, from that point. So what we do is there's infinite amount of them. And in this example, we see that HC is a hypercycle of L. If L is a line, every point on HC is equidistant from the line, right? Horocycles is where, instead of having a line, we have a point which is on the boundary of the Poincaré disc. What that does is it's infinitely far away, basically. And we see that very interesting, where there's the ideal point over here. And the reason why it's called ideal is because we can't really physically make that, because it's going to be infinitely far away. But we can represent that, and every other, this is a perpendicular line. Every perpendicular line on the circle goes to the ideal point. So that's really cool. And another cool thing you can do with that is to make it a periogon. So a periogon is just a polygon with infinite sides. And technically, in Euclidean geometry, a circle is a periogon, because you can have infinite side length of 0. But in this example, it's actually a useful case where we could actually make a periogon with a finite side length. And the angles are the same, and it satisfies everything with what a polygon is. So, we have actually other models to represent parabolic geometry. The first one distorts the straight line, but actually it's conformal. What it means is that it preserves the angles. But in this one, it's the Beltrami-Klein model. And Beltrami is the one guy who just agrees that Euclid is true. And this one preserves the straight line instead of the angles. So you see that the straight lines are straight, but the angles are not accurate. So we usually use Poincaré because angles are more important than straight lines. But this is still...
Last slide, Einstein, basically, it's the idea that this applies to space as well. So we all know this very easy stuff. So the idea is that the gravitational field is just geodesics of stuff falling towards mass. And we can see here like this famous fabric stuff. So mass warps the fabric and the objects follow these geodesics. So 3 nice little facts to end on. So gravitational waves were predicted in 1916, detected in 2015, greater than light speed of black holes, and also 11 kilometers a day is the GPS error without general relativity correction. So this is applying this geodesics knowledge to make you get to your mum's house safely. Little joke to end.